Particular application is that it is graphical in nature. As we just saw in the previous slide, I fit a line through this, I extrapolate that into the future and estimate reserves. It's easy and convenient to apply. It's empirical in nature, as the name suggests. So there's no reference to the pressure or the reservoir heterogeneity involved here, right? It assumes constant operating conditions, meaning that whatever was happening in the past will continue to happen in the future as well, right? Obviously, it provides you with a production forecast. So what are the values or the information that we extract from this particular set of decline analysis? I'll discuss that in the coming slides. What is the limitation? It's non-unique in nature. As I mentioned earlier as well, it's a very subjective topic in the sense that I might feel that a B value of 0 would be good enough for this particular well. My colleague Ankit or maybe somebody from the audience might feel that yes, a B value of 0.2 would be better off. Right? So it depends on your knowledge of the reservoir, it depends on your confidence on to the production data that you've allocated. So it's non-unique in nature, and the EUR is inextricably tied to the history operating conditions. Whatever was happening in the past will continue to happen in the future as well. There will be no operational changes whatsoever. If you want to model scenarios, say I want to have a workover after 6 months and I expect an increase in recovery of say 20%, I can model that as well. So a lot of what if scenarios. Because when you forecast, there's no definite value that you can give to your management or to your company or to the regulatory bodies, right? You always give them a range, a P10, P50, P90 scenario. We all understand what P10, P50, P90 stands for. Optimistic, pessimistic, or in between, right? What is the common best practice? When will you employ using the empirical correlations? So you need to verify as a rule of thumb that you have enough production values. You have enough production being taken out from that well or from that field when you're moving on to empirical analysis. General rule of thumb is the cumulative production should be greater than 50% of the estimated ultimate recovery. First point. Secondly, I don't want to have the decline, the shut-in periods being incorporated as a part of my extrapolation, as a part of my forecast. I don't want to forecast for the time wherein I haven't produced anything from the well. What I'll do to counter that is I'll use a linear curve. Linear means no logarithm, or just a Cartesian plot of rate versus cumulative to see whether I have some shut-in periods or not. I'll just take them off when I match the history. If you're using hyperbolic forecast, so hyperbolic forecast is B value greater than 0 to less than 1. We generally don't recommend you to use more than 10 years of time period for forecasting. Not more than 10 years. You generally end the forecast by the time rather than by ending it with an economic limit. We understand what an economic limit is?
Yes, sir.
What is it?
So the minimum pressure to which you can produce so as to be.
Okay, so it is the minimum pressure, or the minimum pressure is tied to the production value, right? So it is the minimum that you can produce when you have a break even with your operating cost. So if your operating cost is $2 per barrel, if you're getting oil worth $2 per barrel, that is the time you abandon the well. Right? So there are two different ways of ending a forecast. It can be ended by time, it can be ended by the economic limit. These will be there in the questions afterwards. Do not use B value greater than 1. In any case, the results are likely to be very, very unrealistic. You see a B value greater than 1, you don't trust that forecast. Right? Okay, so this is a figure showing you the typical maturity production of a particular well. So after it comes online, this is a log-log plot of rate versus time. So after it comes online, the rate starts to ramp up unless and until it reaches a peak value, the plateau period as we call it most famously. So this is the period that every reservoir engineer or every oil and gas company intends to expand. So I want to have a very long plateau period so that I produce a lot of oil and make a lot of money. After the plateau period ends, the decline starts. So this is the region where you use the empirical forecasting, right? This is the region where your well is flowing into a pseudo-steady state, transients. So Fedkovich devised these curves. This is a still from the Fedkovich paper published in SPE. So these are a set of type curves which you can use to fit your production data and estimate the EUR or estimate the final rate that you're going to produce from this particular well or this particular field. What he did was he wanted to encompass the entire life of the well, not just the decline trends. So he used a couple of flow equations, simple physics, to be incorporated and develop dimensionless rate versus dimensionless time relationships. Equations, if you want to get into, read his paper. This point in time, we are not discussing it. He even stated that B value greater than 1 for this boundary dominated flow region is unrealistic. So this came in 1973, probably 25 years after the ARPS evaluation, right? So this is what Fedkovich developed. After this line, this is from the empirical decline technique. Okay, this is how it looks like from his paper. He assumes a constant bottom hole flowing production pressure as you would find for the most wells worldwide. And it is for radial flow in a finite radial reservoir for a single well model. Okay, so how do you match it in the industry? So this is a still from OFM. OFM stands for Oil Field Manager. It is an application that Schlumberger provides. So this is how we do it in office, right? So this is the production data that I have gathered from the field. This is a set of type curves that I have. Everybody can see it, right? Right?
Yes,
Okay, so what I need to do is, and you can also see there are a couple of, there is a lot of information being mentioned here. So it tells me that you're forecasting for oil. It is a base case meaning no optimism, no pessimism, right? Whatever I see, I'm forecasting. It gives me a B value. As of now, I haven't saved it, so I haven't fitted it to data, so it doesn't give me a B value. I'll move back to the next slide to show you how that is done. It gives you an initial rate when you started off to forecast. It gives you an end time period. It gives you an end rate. What will be the rate when you abandon the well, or when your PSC ends? PSC stands for production sharing contracts. What will be the estimated ultimate recovery? Very important information that is extracted from this particular chart. How is the forecast ended? It has ended by time. The economic limit has still not reached. As I mentioned, you can end it by either time or rate. There are other methods as well, but for you, you can either end it by rate or time. What I do is I just move that data to fit any of the type curves. I feel that this is a good match for me. Somebody else might feel that, okay, this is some kind of an overestimation because this generally shows me a very gentle trend. This is not steep. So someone else might say, okay, I'll go with a lesser B value. So you just fit it to the type curves and you get all that information as was mentioned in the box towards the right. Again, you'll not find this in the textbooks. So the strength is that it's simple and easy to apply. You don't have to know how the pressure is behaving, or you don't have to know how the geology is behaving. A reservoir heterogeneity, if you take into consideration, life will get very tough for forecasting, right? So its empirical nature makes it versatile. So all you need to do is just match it to any of the type curves that you feel is representative of this particular data that you have. It's useful for production data where the flowing pressures are constant or can be assumed constant. So when you flow into the pseudo-steady states, your bottom hole flowing pressure is constant. What are the limitations? It again is non-unique. As I mentioned, I might feel that for the decline part, a B value of 0.1 is good. The other one might say that B value of 0.2 might give me a good estimate. And again, you cannot dissociate that from your reservoir and your production performance. So when you enter the decline trend, whatever was happening in the past will continue to happen in the future. When I say this, I mean it in the sense that it has been showing me a good enough match or a good enough fit for quite a long amount of time. And when I am into the last stages of the well or the reservoir, this is certainly going to guide me as an experience, right? Fedkovich cycles. Okay, are we good till now? Any questions before I move to gas forecasting? If not questions, are you any point that you did not follow till now?
Here we are not considering any kind of flow into the well, like there's no support of water influx into the well.
Okay, so good question. As I said, that the B value is giving you the support. If you choose a B value of 0.4 compared to a B value of 0, 0.4 is likely to give you a better EUR value. That means you're having certain kind of support. I'm not sure if I have it with me or not. I'll just show you what B values to use for different reservoirs. So in case you have a single gas expansion kind of a reservoir, you can go with a B value of 0.3. In case you have an edge water drive reservoir, you can go with a B value of 0.5. Going above that, I personally feel is unrealistic. So B value just shifts your curve to the top, wherein you get a better rate for a long amount of time. So that's how it's taken into consideration. Any other question? Okay. So coming on to the specialized gas forecast, because gas is compressible in nature, I am using a Z value here. Z stands for the gas compressibility factor. I divide P by Z, I put it on the y-axis, I put the cumulative production on the x-axis. As I mentioned that for the case of a gas reservoir, the most of the wells belonging to that particular compartment are likely to show you the same decline trend as a very similar kind of a decline trend. What you have to do is just fit a line through that. This is a very scattered plot. So first you need to identify what all wells are belonging to this particular compartment. Compartment would mean a fluid in place region, something that is bounded by a fault, right? Something of that sort. So if I feel that this is the best fit line for my wells in the entire reservoir, you see there are 46 wells being forecasted here. I extrapolate this line into the future. The point where I have a zero pressure value, the intersection point with the cumulative gas production gives me the original gas in place. This point is theoretical and cannot be achieved in reality because you cannot maintain a zero bottom hole flowing pressure. That would mean your well is open to atmosphere. What you do is you have an abandonment pressure for gas reservoirs. You tell the application, there are specialized applications who can do this. You tell the application that end the forecast when the pressure reaches say 1500 psi. Take this point, mark the cumulative gas production, that is your estimated ultimate recovery. EUR divided by OGIP would give you the recovery factor. Also there is a lot of information that this particular plot gives you. Again, this is a still from OFM as I mentioned, which we use for our analysis. So it gives you that the abandonment is taking place at a pressure value of 0.1 psi, absolute or gauge, you decide. It gives you an EOR value, an original gas in place, and the reserves that you're going to produce from now. Right? Okay, so till now we've discussed how we forecast for a conventional well using empirical or type curves or a material balance equation. What if you have some brand new wells which you want to forecast, or your management is interested to know figures for that? So if I have a brand new well, say this field is flowing up to 2008, if I have a well that came online in 2005, and I want to have a brief or a rough idea about how the trend would be going forward into the future, I can estimate it from this particular technique. So this again is not in the literature. This is developed by one of the principal reservoir engineers in Schlumberger, who sits back in Calgary, Canada. So this plot is an average gas rate per well by the vintage decade. So if the field came online in 1960, I have a vintage decade of 1960s. I have a vintage decade of 70s, 80s, 90s and 2000s. What that means is all the wells that came online during 1960s are shown here in red color. All the wells that came online in 1970s are shown here in green color. It is the average production per well of gas, right? We generally do this for gas reservoirs because they generally show us a similar trend as I just mentioned in the previous slides. Okay, so what I have here is an entire field span of the field in terms of production, right, versus date. I cannot simply extrapolate any of these into the future and estimate my values because I cannot compare them. Something that came online in 1970 cannot be compared to something that came online in 1960, or similarly to something that came online in 2005. What I do is I move them back in time so that all of them start to show their trends right from the first date when the virgin reservoir was hit. So I move everything back in time to say 1960s, and what I have on the y-x-axis now is elapsed days from first production and not date. So as you can see, so simple mathematics or simple physics, this red curve gives me a very stable slope, right? A very stable profile. So the slope here would be less or more? The slope here would be less or more? Less, right? So this gives me a very stable profile, meaning that when the field came online, when I started producing the field, the virgin reservoir, it had a very good amount of reservoir pressure support. That is why I was able to produce a good amount of value. I was able to maintain a better rate. Compare it with this blue curve, which shows me a slightly steep curve compared to the first one, or compared to the green one. And consider this magenta curve, which gives me a very, very steep decline. So these are possibly your brand new wells, because the reservoir does not have enough support now in terms of pressure. So these are the wells that gives you a very steep decline. So this particularly makes sense to extrapolate this trend into the future. What I do then is I just focus on the wells that came online in the 2000s. So I have single plot for each of the year. So 2000, 2001, 2002 and up to date. What I do then is I focus on 2005 and 2007 wells. So the similar curve, I'm just moving back in date to the recent times. What I do then is I match a line through this, I extrapolate that into the future to see for how many more days will I be able to produce this. I already know my economic limit. If the economic limit is not reached, I already know my PSC ending time. So this is a way I can forecast production for the brand new wells that came online, say 2 to 5 years ago. This technique again, how realistic it is depends on your knowledge of the reservoir, depends on how confident are you about the recorded production rates that you have. Right? So this again is a very, very subjective topic. It's not there in the literature, but this is something that we use in-house in case the client asks us to forecast for the newly drilled wells. Okay, so this is the end of the presentation. Now I'll be showing you how we do that in the industry, or how we use this particular information that I was talking about to actually get results. So all these dots that you see joined by, all the red dots that you see are joined by the green line are the production values that you've recorded for every day for a particular well. So this is well number 321. I'm using an alias here. So this is the entire span. It came online in 2000, it is continuing to produce in 2009 as well. What I need to do is I need to understand that what will be the trend that I take forward into the future when I'm forecasting reserves. I can consider a case wherein I take the entire span, I match a best fit and I extrapolate that. So you see there is a lot of value that is being mentioned here. So this is a B value equal to 0. What does that mean?
Exponential.
It means it is an exponential decline. It is very, very conservative. And I'm assuming that it will be a straight line decline going forward. What I'm doing here is I'm matching the entire period. Do you think this particular production value would be representative of what's happening here? I certainly see a drop down in production. Might be due to a couple of reasons. Maybe plugging, maybe say a near wellbore blockage, or maybe some kind of a permeability and isotropy that has dropped in, maybe due to asphaltic precipitation, say. Or do you think this particular region would be representative, similar to this particular region? Certainly not, because you see a spike in production may be attributed to a workover, right? What I need to understand then is, will I be matching this particular region, this particular region, this particular region, or the entire one? So this is where the knowledge of the field or the knowledge of the reservoir engineer comes into play. It is otherwise just a video game kind of an exercise. You match a fit, extrapolate that, get some numbers, present it. What I do then is I feel that after I did a workover, I got a nearly stable profile, and I'm going to use this to extrapolate this into the future. You see all these points before, after and before this have been removed, meaning that this is the only part that I extrapolate into the future. I get a better estimate of EUR here. The other engineer in the organization thinks that no, this trend might not be feasible because we certainly have a drop down in production volumes recently, say for the last 4 years, and I would take this particular stable profile into decline. This again can be right, can be wrong, depends. Or if I say I will not take even this one, I'll just take the last 2 years of production values and decline that into the future. It is for the same well, please mind. And every time you do this, every time you get a different EUR value. So as I said, this topic is subjective and is attributed to your knowledge of the reservoir, your knowledge of the field, and your knowledge of reservoir engineering concepts. Okay, so what is the fun when I just extrapolate that into the future? Anybody can do that. As I said, this helps you drive your economics. So this is 2009. We are extrapolating this to 2014. What if I have a plan to do a workover job, say 2 years after 2009, maybe in 2011. I want to do a workover to this well, and I estimate from my previous experience that it is going to give me, say the acid job is going to give me a 20% increase in recovery. What I do then is I develop a lot of scenarios, say as I mentioned P10, P50, P90 initially. So this is the gas rate for the well. I make a no workover scenario. Nothing will happen into the future. No investments will go into this well. How is it going to behave? So this is a no workover scenario, popularly called as the base case in the industry. What if I do a workover after 2 years and the workover gives me a very good result? So a successful workover. That is my P10 case. The chances are very less that it will decline like this. Or what if I consider a case wherein I do a workover and the workover fails completely? So this is the most pessimistic scenario that